Listo. Okay. Um, so good night, everyone. Welcome to our webinar today. We'll be having as our guest speaker Professor Alexandre Sklo. He's a chemical engineer and associate professor at the Energy Planning Program in the Graduate School of Engineering of the Federal University of Rio de Janeiro tonight. And he will be presenting his talk about is a just transition, just when it comes to limiting fossil fuel extraction. So good night, Professor. Welcome. And this is your space. And on behalf of the SP with the student chapter, we thank you very much. And you can start your presentation whenever you want.
Okay.
Sharing your screen.
Thank you all. Sorry for not speaking Spanish. It's strange for a Brazilian guy speaking English with you that speaks Spanish. I know that that's not the best situation, but I will not try to speak Portuñol or is Portuguese. It's impossible. I will not try that. So I will keep the English. But if you need to ask questions, you can ask in Spanish. I think I can understand. If you speak slowly, I can understand, and I can answer you in English too. That's sorry, my kids just arrived.
It's okay. Okay, just for our viewers, you can ask the questions in whatever language you want. We'll be in charge of translating them and making them reach to Professor Alexander. So please make a lot of questions, take a lot of notes, and Professor will be answering them. So Professor, please share your screen whenever you want.
Yeah, I'm going to share my screen now. Can you see it?
Yes, we can see it.
Okay. So let's start. I'm going to start my presentation by showing you. Just I'm going to remove that. A minute. Okay. I'm going to start my presentation just to show you, showing you my lab, the university, and my research team, and then I'm going to present you the major mathematical models that we are developing in our group, and then some studies related to that, and the study that makes the title of this presentation. So first of all, let's present my research lab. I am in the University of Rio de Janeiro. That's the Federal University of Rio de Janeiro. In the Federal University of Rio de Janeiro, we have this engineering school. The name is COPE. It's the first graduate school of engineering in the Federal University of Rio de Janeiro. And then we have this energy program inside the engineering school. And I am a coordinator of a lab inside this energy planning program. So the Federal University of Rio de Janeiro is the oldest university in Brazil. Actually, it was founded in the last century, but the engineering school dates from the 18th century. So I think this is the oldest engineering school in America, and is now the top 3 university in Brazil. I have some numbers here. I'm not going to read it, but just to show you, this is the second largest university in Brazil and the first university in terms of federal centers of research. And then we have the graduate studies and research in engineering. This is the Graduate School of Engineering. This is a major engineering research center in the Latin American region. A lot of postgraduate courses and master and PhD graduate in engineering, partnerships with governmental institutions in industries and technological companies, but actually a major, let's say a major partnership of this engineering school is associated with the petroleum industry and the Brazilian offshore technological development. So most of the contribution of COPE was associated with the petroleum industry. A few contributions related to the refining, but most of that related to associated with the offshore, deep offshore, and technological innovation associated with this Brazilian ramp up of petroleum production. during the 70s, 80s, and now as of today. And we have also other types of research in copy. For example, this you can see my mouse. Do you see my mouse here?
Yes, yes, Professor, we can see
Okay,
it.
thank you. So this is a train. This is a magnetic train that was developed in copy. This is a wind power plant also installed and tested by copy. This is a bus fueled or running with hydrogen. And we have also some buses running in ethanol with fuel cells. These are some technological development related to the offshore industry. And this is the major tank for testing waves, for testing conditions in the offshore basin of Brazil. This is obvious, this is some development related to solar energy, and also, again, some developments related to the Brazilian offshore industry. This is the energy planning program. I am one of the professors inside the energy planning program. This is one of the listed engineering programs as excellent by the Brazilian evaluation. We have this Brazilian evaluation of the engineering courses, and this is one of the excellent courses as evaluated by the Brazilian agency. And then we have the Cenergia lab. Cenergia lab is a lab inside the energy planning program that is inside the School of Engineering. And we have five full professors inside this lab. I am one of them. And here in this presentation, you can see my basic data, my publications and so on. And we have also this website. So you can see in the website the major research that we have, partnerships and things like that. I'm just summarizing things here. For example, in the lab, one of our major tasks is to develop energy planning modeling tools. So I'm going to present today some of these tools, the most important tools that we developed in our research lab. And by developing these planning modeling tools, we are able, for example, to supporting decision makers and private sectors. As of today, for example, we have some partnerships with the Federation of Banks in Brazil, with a Center of International Research, with some international oil companies that are doing activities in Brazil. We have some partnerships with European centers, with the IFP, the Institut Français du Pétrole. Therefore, we have different types of studies, and most of that are connected, are associated with the planning tools that we have developed in our group. And of course, we are an academic center, so we have the major task of ourselves is to teach and to form new engineers. That's the summary. We are 5 professors. We have some postdocs. We have some PhD students. We have some master students. As of today, we have 8 international projects, most of them associated with the European Union, and 2 national projects. So we are more focused as of today in the international partnerships than in doing research with Brazilian companies. But perhaps in the next years, something will change about that. And we have published a lot of papers in the last 10 or 20 years. So just a summary of our history, but starting to talk about our integrated assessment models. I briefly, I will define the integrated assessment model for you, but just giving the name of them. We have a global CGE model. The CGE model is the computable general equilibrium model. So this is economic model that provides the GDP growth in different countries and have a consistent result for that. So we have a global model for forecasting the economic growth in different regions of the world. This is the T model. Then we have the coffee model. The coffee model is an energy system and land use model that provide a global optimization of the energy and the land use system all over the world for 18 regions. And then we have the national models. And we have a national model for Brazil, of course, which is the blues model. And in the last 2 to 3 years, we have developed a model, the same type of model for Ecuador, as the so-called Elena model. So this is the name of the models, but they have the same type of mathematical structure, the same type of equations, of course, with the features of each country, but the same type of objective function and constraints and so on. And then we have also a model for Peru. So we have 3 national models, and maybe we are going to develop a national model also to Argentina. So our plan is to have some national models for South American countries and perhaps for Latin American countries, because we have already the global model. So we have already a global system model, but we want to have details on the national models for the South American countries. And then we have sectoral models. So we have some models that are focused on specific parts of the energy system. For example, we have an electric power dispatch model for the Brazilian electric system. And then we have also a refining expansion optimization model for the Brazilian refinery system. And these sectoral models provide some results and some constraints for the integrated assessment model. So we have this type of let's say, this chain of models that help us to make some studies and to understand possible pathways for the world, for Brazil, for different regions of the world, and also for some countries inside the South America. The difference between sectoral models and the integrated assessment models is that the sectoral models, they are quite detailed, but they are only focused on one sector or 2 or 3 sectors. For example, we can have a sectoral model to understand and to forecast the consumption of bunker in the international navigation. We have that. And by having this model, we are able, for example, to forecast the routes of the ships, to forecast the type of engines we have inside the ships, to forecast the velocity, the speed of the ships, the condition of the ocean. But we don't have here a model that understands what are the implications, what are the impacts of the international shipping, for example, in the land use. I know that this can be hard to understand, but actually, if we are going to produce, for example, bunker fuels from the biomass, then we can have implications of the international shipping to the land use. We have also implications of the international shipping, for example, in the refining system, in the oil system. And by having this implication, for example, we can change the yield of the refineries, for example, in affecting the production of jet fuel, the production of gasoline, of diesel. And by having that, we can also affect the whole energy system. So we have some sectoral models that only provides results for one sector or for 2 or 3 sectors. And then we have an integrated assessment model that is able to understand the implication of all sectors for the energy system as a whole. And this is important because what happens in one sector can affect the other sectors and also can affect the land use. So this is the major task of the integrated assessment models. These are the major advantages of the integrated assessment models. They are not so detailed as the sectoral models, but they can understand the implications and the side effects of results that happens in one sector for the other sectors. So these are the integrated assessment models. These are the timeline of models that we have in our lab, just to show you that we started that in the 90s. So more than 20 years producing models and starting with very simple models, only focused on the Brazilian energy system. And then having different versions of this model that reached the blues model, which is a very sophisticated in mathematical terms and also in technological terms for depicting the Brazilian and the land use energy systems. And also, we have the Equatorian model as a national integrated assessment model. We have also the global integrated assessment model. So we have the coffee model and the tea model that provide us the situation for the world. And then we have also the satellite models, the sectoral models. And for example, at the end of, as of today, we have, for example, a model for refineries, a model for the electric power system, a model for CO2 pipelines. We have a model also for natural gas integration, for example, in South American countries. But these models are only built for a type of system, a type of sector. For example, the natural gas optimization model is only focused on optimizing the transportation of natural gas, the natural gas supply in Argentina, Brazil, Chile, Bolivia. But we don't have here in this model the implication of the natural gas consumption, for example, for the fuel oil consumption, for the oil production, because this is not the task of this model. This model can run in parallel with the integrated assessment model, providing detailed results for the integrated assessment model. That's our aim in our lab, to run different models in parallel in order to have the best type of forecast, the best type of scenario exercise to understand different pathways for the Brazilian energy system, for the world energy system, and for the South American energy system. And this also, it's important to say that this type of research is the result of different theses and dissertations that were done to improve our model. So we have, sorry, this is in Portuguese, but just to show you, we have theses 2010, and then dissertations, and then dissertation and thesis. And as you can see, we are moving by this chart, and you can see that we are improving the model. We are adding new sectors to the model. For example, 2015, we were only focused on the energy system. And then 2016, we started to have the model providing the optimization both for the energy system and for the land use system. And this is very, very important for South American countries, not only for Brazil, but also for Ecuador, for Colombia, for Bolivia, for Argentina, because the biofuels are very important for these countries. And also the food production, as you know, is very important for Brazil, for Argentina, for Ecuador. And then we can have some competition and some implications of the energy production and the food production and the cattle. And these are important to have this simultaneously inside the models. So these are the type of development that we have done in our integrated assessment models. Then we have, for example, here, carbon capture. And then we have this balance of CO2 also in the model. So we started with the energy system, then the land use system, and then the CO2 and the balance of CO2, because most of these integrated assessment models needs to be run to answer a major question. How can these countries deal with deep decarbonization targets, with the mid-center decarbonization targets? So these are important for us. And then we have this option of capturing CO2. Also, by 2018, we added also the water balance in our model. So now in our model, we have the energy balance, the food balance, the land use balance, and also the water balance. Why? Because, for example, in the case of Brazil, we need water for the hydropower, we need water for food production, we need water for cities, we need water for industry. So water is a constraint. And if we don't have water, if the planning of the water is not so good, for example, this will affect the hydropower production in Brazil. And by affecting the hydropower production in Brazil, this will affect the natural gas power generation plants. And by affect this plant, they can affect also the industrial sector in Brazil and so on. So these are the connections that we have in the energy system and that we have to implement in our models. So this is our type of situation here. And at the end of this presentation, I will talk about some tasks, some future problems, some challenges that we have in the near future. And these are some international partnerships that we have in our lab now. And as you know, most of that are located in Europe, for example, in the Netherlands, in France, in England, but we have also some partnerships in South America too. And particularly, we have this partnership with Escuela Politécnica Nacional. Sorry for my Spanish, but this is a partnership that provides us the possibility to develop the Equatorian model. And we have also some partnerships specifically related to petroleum. And that's the case of the Institut Français du Pétrole, the French Petroleum Institute. And we have now a major partnership with this center of research in France, and also some centers in USA and in South Asia, Southeast Asia. So let's start. That was just a presentation of my lab. Very briefly, and just to show you something about the lab and the type of models that we developed and why we developed these models. So let's talk about a little bit more about the modeling platforms. So let's talk about the integrated assessment models. That's the acronym, the integrated assessment models. And let's talk about the T model, the COF model, the BLUES models, and a little bit about Elena. Elena is the youngest integrated assessment model of our portfolio. So that's the type of linkage that we have for our integrated assessment model. So we have the T model is an economic model for the world. And by running the T model, we can see, for example, the food demand in Europe, the food production in South America, in Brazil, the food production in the USA, the energy demand in the USA, and so on, and the GDP growth and the demographic situation for the world is split in 18 regions. Then the T model provides the economic scenarios for the coffee model. The coffee model is the world energy system model. And we run the coffee model in order to have a best portrait of the energy system for the same 18 regions. And the coffee model provides for the national model, for example, for the BLUES model, the constraints. By running the coffee model, we have, for example, the price of the international oil price, the international natural gas price, the coal prices, the fuel trades, and the food trades also. And by doing that, we have the constraints for the national Brazilian model, for the national Equatorial model, and perhaps in the near future for the Argentinian model. And we can run the blues model in a consistent way. So we have a consistent, because we have here the world economic, then the world energy system, and then we have the blues model as the national model. It's important to say these are the global integrated assessment models. As you can see, we have more or less 10 integrated global, 10 world integrated assessment models. And it's a pity because only one is below the equatorial line. Only one does not belong to OCDE countries. And this is the coffee model, the model that was developed by us in Brazil. So this is the same type of information. You can see the major global integrated assessment models, and we have here, we hope that we can have this in other global South countries, but as of today, only us ourselves we have this model. And it's important to say why we have developed this model. We have developed this model to get global results. We need to understand and to make by ourselves the projections of the world, and also to have a model that can represent in a better way Brazil and South America. But because most of these global models do not focus on the South American countries. So it's important for us to have a world integrated assessment model that has a good representation of a region, of our region, and then to provide information for a national Brazilian model. That's our target. Then we have this global T model. I will skip that. I can answer some questions after the presentation, just to show in something here. I don't want to be to spend much time on that, but this is an optimization model running on GAMS. The language is the GAMS, and we have this general equilibrium model. These are the sector inside the T model. Then we have the coffee model. The coffee model has a time horizon up to 2100, 18 regions in the world, and is for the energy system and for the land system. This is important, completely integrated. So the objective function is built to match the demand for the energy services and the demand for food, not only the demand for energy. These are the 18 regions of the coffee model. We want to split more the South America region, but as of today, we have Brazil and other South American countries, and these 18 regions. Some global integrated assessment models, they have, for example, Latin America and South America all together. And for us, for example, we can see here that we tried to have a better representation and to also to have Brazil inside the world. We are a Brazilian group. This is the type of chain that we have in the coffee model. This is the type of data that we have to provide to the model. So for example, here we have a production cost and the ultimate recovery resource of oil, of natural gas, of coal, of uranium. And then we have this type of production cost in order to understand and to forecast, given the demand, the type of price that we have in the model and the type of resource that we are going to produce in the model. Of course, the model will run as a competitive market, but by constraining the model, we can force the model to have some oligopolistic behavior. But by not constraining the model will run as a competitive market. This is the land system representation, very simplified inside the model, but it's important to say that we have this transition of land, then we have forest, pasture, croplands to produce foods, and importation, exportation. So this is the transition of land inside the model. As you know, most of the Brazilian GHG emissions, greenhouse gas emissions, comes from land use change and agriculture activities. And this is the same for Ecuador. I don't know if it's the same for Colombia, but it's the same for Ecuador. More than a half of the GHG emissions in Ecuador cannot be explained by the energy system, by the fuel combustion. Most of that comes from land use change. So if you are going to run the model to cope with deep decarbonization targets, we need to have the representation of the land system. So we have this representation inside the world model, but also in the national models. And that's the type of land use structure that we have. For example, by converting cropland in planted forest, we are capturing CO2. But by deforesting to produce more food, we can emit some CO2. So this is the type of transition metrics that we have inside our model that will give us, for example, CO2 emission from transition, energy consumption from transition, land use change from transition. That's the type of result that we have. And also, as I told you before, this is the balance of CO2 if you will want to capture the CO2 and then storage the CO2, for example, in some geologic centers and things like that. Same thing. And then we have the global model providing data to the national model. For example, resources, energy and food products trade, international oil, coal, gas, uranium production cost. And we can run now the national model. For the case of Brazil, the national model is called BLUES model, the Brazilian Land Use and Energy System model. It's a model that is split in 5 regions, load curves for 12 months, 24 hours. So it's pretty much more detailed than the global model, of course. And we have specific technologies for Brazil, the same for the Equatorian model, and a very detailed representation of transportation, industry, residential service, and so on. That's the type, I know it's hard to see that, but that's the type of structure that we have in the model. For example, in the industry, this is the type of structure that we have. We need to produce, to output, for example, a industrial product. And we have here in this example, 2 processes, different types of equipments, of devices, and different types of fuels or energy carriers. And the model will follow all this chain in order to, for example, output iron, output chemicals, and so on. For example, we have 2 types of process to produce cement, and we have different devices in this process, and we have different energy carriers, and this is the type of structures that we have for each product, each industrial product in Brazil, and the same for buildings, and the same for transportation. And by doing that, we have at least more or less 12,000 technologies by macro region in Brazil. And this is a type of structure that we have in the model. And the idea of the model is to have the optimization of the energy system and the food system to cope with a demand, but not a demand for gasoline. It's a demand, for example, for mobility, for passenger kilometers, for example, for cement, for iron, for petrochemicals. And we are going to run the energy system in order to do that. And for example, if we want to have more mobility, more urban mobility, in the model, we have the light duty vehicle fleet running by gasoline, running by ethanol, but we have also the possibility of electric vehicles, hybrid vehicles, fuel cell vehicles, and the model in the long term has the option to decide, given the cost of the technologies, the efficiency, the technological features, and the investments constraints in the system. That's the same time, this is the representation of the Brazilian land system, just to show you that we have this representation of the type of land that we have in Brazil, but the same, for example, in the Equatorian model, the Helena model. So we have the same type of structure, but different data in the case of Equator. And this, for example, I have shown to you the representation of the Brazilian land use system. And this is the representation of the Equatorian land use system. So the same type of structure, but with different data and different solutions, of course. So let's start with the aim of our presentation, showing you two types of results that we have in our types of models, our integrated assessment models. First of all, an example of land energy nexus, a type of study that we done for example, understanding how the deforestation of Brazil can affect the Brazilian climate mitigation strategies. Just summarizing that, let's say that Brazil has a deep strategy for decarbonizing its economy. But then Brazil is now emitting by land use change, by deforesting. By doing that, we are already emitting GHG. And therefore, we need to understand how the energy system, how the industrial sector in Brazil can compensate for that emission that comes from deforestation. And that's the type of study that we have implemented in our integrated assessment models. And we have wrote a paper. The name of the paper is The Threats of Political Bargaining to Climate Mitigation in Brazil. Why that? Because political bargaining in Brazil means that we are reducing the command and control policies for controlling deforestation in Brazil. And by doing that, we are increasing the emissions by land use change. And therefore, we are going to need to compensate for that in the energy system. So again, we run the world energy system model in order to understand how much Brazil can emit in the case of a 2-degree world. That's the Brazilian budget. That's the kind of constraint that we have inserted in our national model. But these are the type of forecasts that we can have for land use change in Brazil. For example, in Amazon and Cerrado, in Savannah. These are forecasts. So this is the worst situation, and this is the best situation. As of today, Brazil is going by that. Brazil is more close to the worst situation in terms of deforestation. And by doing this type of pathway, Brazil is going to emit CO2. And we'll have Brazil, perhaps, is going to have to compensate for this emission. So this is the type of forecast that we can see in our model. The deforestation in Brazil because of reducing command and control policy for land use. This is not the historical situation. This is a kind of catastrophic forecast. And by having this catastrophic forecast, I know it's hard to see, it's hard to understand here, but I'm just showing that in blue here, this is the budget, this is how much Brazil can emit here. With strong policies related to deforestation, we have space to emit in the energy system. For example, producing more oil, using more fossil fuels. With weak deforestation policies, with weak controlling deforestation for policy, the space of the energy system is very low, meaning that Brazil has to switch the way Brazil is, for example, using gasoline, diesel, and bunker and jet fuel, because Brazil has no space for emitting from fuel combustion. So this is a type of study that we can see that can be done by ourselves in our model. And this can answer, for example, the type of fuel that we are going to need to replace oil products. And for example, we can see here, we are going to produce, for example, ethanol with carbon capture. We are going to produce, for example, diesel from biomass to liquids, diesel from Fischer-Tropsch synthesis. We are going to need biodiesel. We are going to need kerosene from biomass. So these are very, very advanced biofuels, very costly biofuels, and needed if Brazil wants to decarbonize its economy, but has to deal with the deforestation that is happening during this decade in Brazil. This is another type of study that's the name of our presentation here. This is a study that we have presented in the USA this year. And the idea of this study is to understand the case of the stranded reserves. The meaning that in a decarbonized world, for example, during a green recovery of the economy, we are going to have some reserves that cannot be extracted. I know this is a type of wrong definition, because if it is a reserve, this means that we can extract these resources. But we had some reserves that can be extracted given the price of oil, given the technology that we have. But because of the CO2 constraint, during the next 50 years, for example, they won't be extracted. And by that, some countries will hold some stranded resources. In this can, for example, result in conflicts and also perhaps some economic diversification. Some countries say that the world should need to allow poor countries to continue producing their fossil fuel reserves. And there are a lot of explanations for that. For example, some poor countries say that we have these fossil fuels, we have these reserves, and we didn't emit a lot in the past. So maybe for this compromise to reducing the GHG emission, because of the equity principle, this is not my argument. This is the argument of some countries. Because we are not responsible for the past CO2 emissions, we should have some allowance to emit more in the near future. And by doing that, we are going to extract part of our fossil fuel reserves. There are some experts that discuss this concept of equity. So there are some countries that say, this is a justice. We are not responsible for the CO2 emission of the past, so we should be allowed to produce a little bit more in the near future. But some experts say that this is not justice because, in fact, for some countries, the extraction of fossil fuel resources may lead to the strengthening of the democratic regimes, for rent seeking, for concentration of wealth. So when we talk about, for example, a country, we are not talking about that what is inside the country. And for some experts, for example, I'm citing here, I'm referring here, Stiglitz. For some experts, they say that there is no real wealth in just extracting fossil fuels. We can discuss this later, but this is two types this is a type of debate that we have now in the scientific community and in the political forums. But the important thing here is that we have run our model, our global system model, the coffee model. First of all, freely, we are going to produce oil, natural gas, and coal without forcing the model to, let's say, to cope with equity allocation rules. Then we are going to run the model and we are going to force the production of oil, natural gas, and coal in these blue areas, meaning that they will have a type of allowance to produce more fossil fuels because of the equity allocation criteria. They are a concept of the allocation criteria. We are going to run the model in order to cope with the Paris Agreement. And in the Paris Agreement, the idea was to have a world reaching or compromising to a well below 2 degrees, meaning that we are going to control the increase of the temperature, in the case of our model, to 1.5 degree. And by running the climate models, this means that the CO2 budget, the CO2 the carbon constraint of the world energy system is more or less 400 for 2100. That's our budget. And we have 4 types of scenarios here. A scenario without any carbon constraint. A scenario with the carbon constraint, but not having these allocation criteria. So the oil will be produced by the least cost producer countries, not by the countries that says that they have the right to produce more oil. And then we are going to see 2 types of alternative scenarios that force the production in the selected regions that I showed you before. These selected regions, I'm going to force the production in these regions. How we are going to do that? In the first case, we are going to allow the production that we had in a world without carbon constraint. So these countries will be allowed to produce the same time. This is a top constraint. This is a type of constraint that allows these countries to produce the same type of oil, natural gas, and coal that they will produce without carbon constraint. And in the second case, the same thing, we are going to allow these countries to produce more oil, natural gas, and coal than they will produce in a global least cost solution under carbon constraint. But now our criteria is that these countries can produce their 2P results, their proven plus probable results. And the fossil fuel here, of course, means crude oil, natural gas, and coal. That's the type of results that we have. And for us, for example, in the case of these scenarios, for the current production without carbon constraint, these selected regions are going to produce this amount of oil, natural gas, and coal. With carbon constraint, they are going to produce less oil, less natural gas, and much less coal. For the first case, allowing them to produce the same of the current policy, this is a fixed constraint, so they are going to produce the same type of production that they had without constraint. This means that because these regions are going to produce more, other regions needs to produce less in order to cope with the world carbon constraint. That's the answer that we have in the model. We are going to see which type of oil is going to be replaced because of this allowance. And in the case of the allowance to produce the proven and probable results, we have pretty much the same type of results that we have in the first situation. This shows us the whole world, and this is the production of oil, the cumulative production of oil. As you can see, this is the production of these countries without carbon constraint. By having the carbon constraint, we need to produce less oil because of the carbon constraint, and these countries are going to produce less oil, of course. Then we have the allowance, and by having this allowance, these countries produce more in the detriment of the rest of the world. The same happens in the natural gas and in coal. So the same type of result we have, and we are able to understand, for example, in the production curve, for example, here, we can see that some production in the selected countries are more expensive, means have crudes also, so are more expensive to extract, to develop, and are more expensive to refine. But they are forced to be produced because of our allocation criteria. By seeing that, we can, for example, understand what happens to compensate for that. And for the compensation of that means that we are going to need more net negative emission technologies, for example, more bioenergy. We are going to need more solar, nuclear, and electric vehicles. Because we are producing less quality oils, we need, for example, also some revamps in refineries. We are going to produce heavy crude, so some refiners need to invest to cope with this lower quality of the crudes. But also because of that, these refineries are going to emit more CO2, and this CO2 needs to be compensated in the energy system. So just finishing here, the type of research that we are doing now in our research lab, we are improving our satellite bottom sectoral models in terms of oil refining, petroleum production, natural gas value chain. And of course, we are improving now the representation of petroleum production in terms of quality, in terms of production curves in the world, in different regions of the world, in terms of the 18 regions of our tools. We are improved the land use modeling, and now we are having some balance for fertilizers and chemicals, and also seeing the land intensification rebound effects. And we are now also developing, for example, a material supply and demand model inside our integrated assessment model. The idea here is that some materials constraints can interfere in the pathways that we are seeing in our scenarios. And also, we want to strengthen international partnerships. So, for example, we just submitted a project with some colleagues of the Argentinian Fundación Bariloche in order to get some funds to develop national models for Argentina, and then to have more models running in the South America in order to provide support for research centers, for academia, and for national governments to develop strategies in the long term. Thank you. Sorry for this long webinar. I'm here if you have some questions.
Okay, can you see me there? Thank you very much, Professor. We have some question here. Can you hear me?
Yeah.
Okay, perfect. So the first question is from Carlos. He's asking this. What incidence do you consider that has the clean energies on single model for oil energy systems?
Sorry, I couldn't understand the question of Carlos.
Okay, my bad. Carlos asked, what incidence do you consider that has the clean energies on single model for oil energy systems?
I'm not sure that I understood the question of Carlos, but I am trying to answer. And then, Carlos, if you have a different understanding of your question, please explain me. Really, as of today, most of the oil products or the oil products market, and the petroleum industry needs the oil product markets, of course. And most of the oil product markets are concentrated in transportation and in petrochemicals production. We have some market for electric power generation, but most of that was replaced after the 70s. And this means that petroleum products had a captive market in the history for transportation and materials. But as of today, there are some contestation for this market, especially for urban mobility, because of the electric vehicles, for fuel cell vehicles, and the need for controlling atmospheric pollution and greenhouse gas emission. This means that by electrifying the mobility, petroleum products will start to compete with some renewables. Also, there are some captive markets for the petroleum products for aviation and for international shipping. But as of today, the International Maritime Organization, IMO, has set some very stringent targets for the GHG emissions of shipping in 2050. The target is curb the GHG emissions of the international navigation by half in 2050, giving the emissions in 2080. This means that the activity level will increase, but we need to have the half of emission of 2008 in 2050. And as of today, there are a lot of research in Europe, in China, in Brazil, in Japan, related to alternative fuels for shipping. Therefore, some alternative fuels, for example, means ammonia, biobunkers, hydrogen, cleaning the energy matrix and contesting and challenging the captive markets of oil products. Actually, the oil was in a very, very safety situation because coal compete with PV, with wind power, with natural gas. Natural gas compete with biomass residues in the industrial sector, with coal, with hydropower, PV. But gasoline has no competition in most of the world countries. Diesel has no competition. Jet fuel, bunker, petrochemicals. And this is slightly changing. And that's perhaps the idea that the clean energy will start to challenge the petroleum system, the petroleum industry. And that's the problem. Most of the experts are now talking about peak demand for oil, not peak supply. And they are talking about a peak demand in 2050, 2040 because of that. So we are going to have some supply of oil as it is with coal without demand because of the replacing of some oil products.
Okay, thank you very much, Professor. We hope Carlos got his question answered. And next is Luz Dari. She asks the following: the capture and storage of CO2 has been gaining momentum, as it would allow humanity to remedy in a certain way its footprint on planet Earth. But how could countries like Colombia develop this important technology and not be left behind with respect to pioneer countries?
Actually, the carbon capture is gaining momentum in terms of R&D and in terms of expectations. But we have, as of today, less than 20 major facilities capturing CO2 in the world. And most of these facilities were already capturing CO2 because of traditionally they capture CO2. That's the case of urea production. That's the case of some natural gas production facilities. Therefore, we are in the beginning of this technology. We have some expectations, and it's gaining momentum because we need to curb emissions, and their emissions are growing. We need to curb GHG emissions, and the GHG emissions are growing. So we know that renewables will not be sufficient to control the GHG emissions for the target, for the Paris target. And therefore, there are a lot of expectations related to CO2. This means that Colombia can reach the momentum, can have the momentum. The point is, Colombia needs to understand which type of CO2 capture is important for Colombia, because CO2 capture is a world. We can have CO2 capture, for example, in the natural gas production. We can have CO2 capture in the coal combustion. We can have CO2 capture in petrochemicals production, in the cement production, in the biomass conversion. So the idea here is to understand which is the most strategic focus of Colombia on CCS, not all CCS, and also to understand the storage sites of Colombia also, because Colombia has some sedimentary basins that were depleted. And some of these depleted sedimentary basins can store CO2. So perhaps understand the CO2 chain and the strategic position of Colombia for the CO2 chain, but not for the whole CO2 options.
Okay, thank you very much, Professor. And for the final question, we have Daniela Martinez. She asks, what is the biggest limitation of the integrated evaluation model?
To be a model, the big limitation of a model is that a model is always a simplification of the reality. And the biggest limitation of a model is the expert. I don't know if it's understandable by you, Daniela, but it's Daniela, isn't it?
Yeah, Daniela.
Daniela, yeah. Sorry for my Portuguese way of speaking, Daniela. But actually, Daniela, there was a mathematic, a very, very known mathematic that says that we have to use model as a drunk use the light, not by the light, but by the support. And this means that the major problem of a model is that a model tests is assumption. The model wants to show you some possibilities, but the experts, they are needed to understand and to use the model, and also to understand the simplification of the model. No model can represent the reality, and the reality is very complex. We have non-linearities, we have behavior. For example, we have the simplification of behavior inside all models. And what we have in these models is a kind of what if situation. We need to understand, for example, if the world wants to have more hydrogen in ships, how the energy system can be arranged and what are the implications of that. For example, we have the scenario of Shell. Shell has a scenario called Sky. And in the Sky scenario of Shell, there is a lot of hydrogen that is produced from water electrolysis. So they have solar PV, water electrolysis producing hydrogen, and then the hydrogen being used, for example, in aviation. This is the scenario of Shell. And they presented this scenario, for example, for our group in COP. But they don't have this integrated assessment model. They just have a type of simulation model without seeing, for example, the water constraint. And for producing the hydrogen in the water electrolysis, you're going to consume water. And the water is more rare than the oil. We have more problem related to the water availability than related to oil availability. And also, we are going to need some electrolyzers that can cope with the intermittency of the solar PV, because the solar PV runs like that. And the chemical reaction cannot run like that. So we are going to need some batteries. And we asked them about that. And they told us, we don't thought about that. We just want to produce hydrogen. And we have water, we have solar, and then it's okay. So the idea is there is no perfect model, but there are models that can help us to see our limitations. So the basic target of a model is to control our wishes and to show us our limitations and the limitations of the world, and also the limitation of the model. But the model help us to understand these limitations. That's my point.
Okay, Professor, that will be all the questions for today. So with this, we can get for finished our today's webinar. Once again, on behalf of the SPWIS student chapter, thank you very much for your talk. I hope and I know that many of our viewers here enjoyed it and will take a lot of advantage of the knowledge they got today. So thank you. Thank our participants, our viewers. And yeah, thank you very much.
Thank you all. Thank you all. We had some very nice students from Colombia in our lab, from Ecuador, from Peru, from Argentina. It's always for us, it's a pleasure to share this information and this type of activity with you.
Thank you. The
So
pleasure.
for us, have a good night.
Have a good night. Think big, think smart, think SP.
Okay.
Listo,
Thank
Diego.
you. Thank you. Bye bye. Ciao.
Gracias. Thank